Okay, so today we will review some materials we learned in the past few weeks, and hopefully we can move a little bit more. But this chapter actually is a little bit difficult, so I have already slowed down my lecture speed. Okay, but I hope maybe we can have more examples to show you and implement these examples in R coding. Okay, so on the other hand, I also revised my materials a little bit because of some errors and mistakes I made in the past. So I just upload the materials this morning with a revised edition. Okay, so let's check out the revised handouts. Now I tell you where I revised my materials, and basically these are not that important, but I think I can highlight the points I made or revised so that you can capture the key points quickly. Okay, just a minute. Okay, so I revised, there are two slides, okay, machine learning, financial data analysis classification. This is about the logistic regression. Actually, we talked a lot about the logistic regression already, but I want to show you that some mistakes I have made, and actually I have revised the mistakes. So nothing big here, but let me show you here. Okay, I changed the title. Okay, so this slide is focused on logistic regression. Honestly, logistic regression is widely applied in finance. For example, like we do see a lot of trading signals in financial market. For example, like when we should buy or when we should sell the stocks. Okay, and besides that, we also have many features to consider. For example, maybe you can include as many features as you like, maybe some technical indicators or such as the RSI moving average, trading volume, and the rate of return in the past few weeks. Okay, or during the past certain period of time, whatever. So you can include as many features as you can. But we call this as a features, and this is also called the explanatory variables in regression. However, we also have output. Okay, the output is yes or no. So this is a very basic methodology in logistic regression. So and then we also need to measure the probability of increase or probability of decrease in terms of the stock index or market index. So this is the basic logic or methodology behind logistic regression. So don't get yourself stuck in the examples outlined in the slides, because in the slides I will use a very standard database. For example, like the default is data in the banking. Okay, default data in the banking. But of course, this is also important information or database for finance students. But most of the time, I like you to apply what you have learned in this methodology to the financial market. In other words, to get, is it possible to get a higher winning rate, okay, in your trading, okay? So I think that would be more interesting and more realistic. So this is about the logistic regression. And of course, here we also consider other issues we discussed before, like the linear discriminant analysis, quadratic discriminant analysis, naive Bayes, and the k-nearest neighbors. Okay, so this is what we have learned. So logistic regression is a starting model for discussion on generalized linear models, okay, including Poisson regression. Okay, so let me skip this. Okay. So what I revised here is this part, okay. Okay, so the logistic regression assumption of the model. Okay, there are several assumptions of the model. The first assumption is the outcome is binary, and of course this is referring to the outcome of yes or no. Okay, default or non-default, or buy or sell. Okay, so basically this is a binary. And the second thing is how to interpret the results. Okay, how to interpret the results. So the log odds of the outcome, okay, basically this is the log odds of the outcome, but honestly, this is very difficult to interpret. So we have to transform the log odds, okay, into probability of odds ratio. We tend to use odds ratio, okay. But what we are discussing here is the assumption of the model. Is that the second assumption is that log odds of the outcome independent variable have a linear relationship. Okay, so linear, we are assuming that the log odds of outcome independent have a linear relationship. So how to address it, or we how to prove that there's a linear relationship between the log odds of outcomes and independent variables. Okay, so we can, like linear regression, we can play around with the square or cube terms to see if they address the curve relationship in your data. So you can use this approach to verify there exists a linear relationship. Okay, and the third assumption is errors are independent. Okay, we also assuming that the errors are independent, and of course sometimes we have some problems like obvious clusters in our data. Okay, so if we have this kind of concern, then we can adjust it. We can run the logistic regression, adjust it for clustering. Okay, using cluster robust standard errors. Okay, but we haven't covered that yet. Okay, so this is just to let you know that, okay, if we have the concern for clusters in our data, then we probably need to use cluster robust standard errors. Okay, so the last assumption is there's no severe multicollinearity. Okay, so this is the same assumption by the linear regression. We don't like to see any multicollinearity. So if we have this kind of concern, then we can run a VIF, okay, which is variance inflation factor, to detect the correlation between our independent variables. Okay. So in the following are the differences to linear regression assumption. Logistic regression and linear regression belong to the same family models, but the logistic regression does not require an assumption of homoscedasticity, or that errors are normally distributed. So we don't have this kind of assumption like required by the linear regression. Okay, so in this part, logistic regression is more flexible than traditional linear regression. Okay, so this is just for your reference. I also posted the reference link so that you can check the link. I think the link is very good because this book okay, you can check the link as well. Let's have a very quick brief of the book. This book is completely focused on the categorical regression. Okay, so if we go to the top here, we will see that this is categorical regression theta in R. But basically these examples, which means these examples can be implemented in theta in R. But we want to use R. So let's, it's very good to have R codings available. So let's just look at the contents here. Okay, so you can see we have linear probability, logistic regression, etc. Okay, but I think more interesting thing is that this book contains the multinomial logistic regression, the multinomial log regression, and I think that will be more interesting in the future in classification issues, in solving classification issues. Okay, so this is the book completely focused on categorical regression. Okay, so this is just for your reference. And okay, so I just referenced some part of it. And then I also added logistic regression pros and cons. Okay, so there are some advantage and disadvantage. The pros, you can interpret the odds ratio easily, okay, by running the logistic regression. So that logistic regression are the most okay. So the logistic regression is the most common model used for binary outcomes. But there are some disadvantages. That means it's not very easy to interpret the results. Here we have odds ratio and log odds are not straightforward to interpret as the outcomes of linear probability model. So sometimes we need to become more familiar with the results and understand how to interpret the results. Okay, so this is about the other issues, like we have different ways to interpret the results. Just like I mentioned, we have odds ratio. We usually use odds ratio, and also we can also use the predictive probabilities, because logistic regression can generate the predictive probabilities. And then, of course, we also have marginal effects. Okay, so down here, okay, you can check the results. Okay. So here, I didn't change much. Okay, basically it's still the same as you saw before. Okay, so here I also include okay, sorry, this is the file name here. Okay. So here is about how to generate the predictive probabilities. So you have to understand how to generate the predicted probabilities based on your input data. Okay, so here's another example to predict the probabilities of employee attrition. Okay, so this is another example. So down here, are the examples about the predicted probabilities with all other variables held at the means. Okay, so this is just for your reference, because here we are using the function. Actually, the library is called the ggfx, and we are using the ggpredict. Okay, so you can see the predicted probability of the default based on different levels of monthly income. Okay. Okay, so in the following, about assessing the model accuracy, we have the following three models. Then we need to be able to assess the model accuracy. Now we have three models, so we need to compare their prediction accuracy. So here are the codings. Okay, just for your reference. And basically, I just, because I made some mistakes in the numbers, so I just corrected. So now you can see this is the accuracy. So you can see we are using the summary, okay? And we have model 1, model 2, model 3, and accuracy. So now I'm using I revised the number, okay? To be consistent with the output of this coding. Here it shows that model 1, model 2 are 83.95%, okay, in terms of accuracy. However, if we are using a model 3, which used all predictor variables in our data, then we will achieve an average accuracy rate of 87.50. Okay, so this is model 3 accuracy. Okay, so that means model 3 outperforms model 1 and model 2. Okay, but this is just accuracy, sample performance. We need to implement these models in the test data. Okay, basically this is the final step that we need to verify. So this is just for reference. And of course, other metrics, okay, to measure the prediction accuracy, such as the confusion metrics. Okay, we mentioned that before, so I'm gonna skip that. Okay, so this is the metric, confusion metrics. To generate the confusion metrics, we have some functions available. For example, like we can use the confusion metrics here. But if you search for the confusion metrics in R, you will see many different packages providing similar functions to generate confusion metrics. So you are not limited to using this function only. Okay, maybe you can find the different functions to help you to generate the confusion metrics. So here is just one of the many examples to show you how to calculate the confusion metric. But of course, you still have to provide some input parameters. For example, here we have data and the reference. Okay, but don't get yourself frustrated with these functions, because you have many examples on the internet so that you can reference, even though you can also calculate it by yourself. Okay, I will show you some examples later. But basically, what we mentioned before is about the known information rate. Okay, so this is 83.9%. So this represents the ratio of non-attrition versus attrition in our training data. Okay, so this is about the confusion metrics. Other metrics like ROC curve, we call this receiver operating characteristic curve. That's a representation of a classifier's performance across all possible decision threshold. Okay, so Now we have a issue about the decision threshold. If we are more concerned about the risk, maybe we can raise the decision rate threshold to a higher level. Okay. So down here, we can see the results here. Okay. So now you can see the ROC curve for the cross-validated Model 1 and Model 3. So you can see the increase in the AUC represent the lift that we achieved with Model 3. So that the blue line, the higher the blue line, which means the area under the blue line is larger. That means that the higher accuracy this model can provide. Okay, usually we use the ROC curve for cross validation. Okay, so here are some codings to generate the ROC, so you can check by yourself. Okay, then we also have a PRS logistic regression called this is a partial least square logistic regression. Because we like to reduce the dimension of our numerical predictor, okay? In the traditional regression analysis, we will use the principal component analysis. So similarly here, we try to decrease the dimension of the predictors. Okay, so if we can decrease the dimension of predictors, and in the same time we can also maintain or improve the accuracy of prediction, so that will be good. Okay, so based on this, we can generate this PRS logistic regression here. Okay, so you can see x-axis is the number of components. So you can treat this as just like the principal component. Okay, but on the other hand, you can also treat this as a number, not dimension of our numerical predictors. Okay, so in this case, we can see that the number of components, optimal number of components is 11. Okay, so you can see there's a red arrow here, pointing at here. So that means that we can achieve the accuracy, okay, at the maximum level with just 11 components here. Okay, so this is another matrix to help us to determine the dimension of numeric predictors. Okay, so there are some other model concerns. So this is just for your reference, but with this issue are still developing, so you can see some recent papers, okay, discussing this issue. Maybe some papers are more interested in the residual analysis. Okay, so here are some of the papers like the 2018 Liu and Zhang, okay, introduced the concept of surrogate residuals that allows for residual-based diagnostic procedures and plots, not unlike those in traditional linear regression. But these are more advanced papers, okay? But if you are not so interested in machine learning issues, okay, this is not required for you to read it, but just for your reference, okay, there are some newly developed skills out there in the literature. If you want to apply these techniques to your prediction model, okay, for example, most of the time we like to increase our prediction accuracy about the stock price, okay, rise or decrease in the future. Maybe we can apply this approach. Okay, the following are the same. I didn't change much here. This is about the feature interpretation. Okay, so here describes 20 features Okay, 20 features. So we have many features to predict the attrition. Okay, job attrition. So we need to identify maybe 3 or 4 most important variables to explain the job attrition. So here you can see here from the top, overtime. Okay, overtime is the top ranked feature to explain the attrition. The second is job satisfaction, and third is environment satisfaction, and third is environment satisfaction. Okay, so basically environment satisfaction is very important. These factors are ranked third and fourth among our 20 features here. Okay, so this is for your reference, and then of course here we are using the VIP function. Okay, you can use VIP function to generate the results. Okay, so we can also use another way to show the probability of attrition, the relation between the probability of attrition, the relation between the probability of the attrition and the features. Okay, so we are using what we call as a partial dependence plot, which is PDP. Okay, so PDP, we using PDP, we can visualize the relationship between model features and their target variables. They can tell us if a relationship is linear, non-linear, or if there's no relationship. So you can see here, figure 5.7 illustrates the functional relationship between the predicted probability of attrition. So the target variables now is the predicted probability of attrition, okay, and the number of companies employees have worked. So we can see down here. Okay, if you check this plot, okay, this is about the, so now you can see the y hat is the probability of attrition, okay, and the axis, because there are 4 plots, so now we have overtime, okay, variable, and the job satisfaction, and go to the bottom here, we also have number of companies worked, and the environmental satisfaction. So we selected 4 variables. Okay, maybe these four variables. Okay, these 4 variables are the most important variables here. Check here. Okay, overtime, yes. Okay, job satisfaction, environmental satisfaction, very high, and number of companies worked. So these 4 variables features are selected. And we want to see their relationship with the target variables, which is the probability of attrition. So based on this, then we can analyze their partial dependence. Okay, so this may give us a more clear picture of the relationship between job attrition, probability of job attrition, and the features we are interested in. Okay, so this is also important, partial dependence plot. Okay, so this is the first slide. I just revised, and I just highlight some points here. Okay. So these materials are based on the reference of hands-on machine learning wizard. Let me just show you here. You can just type hands on machine learning wizard. Okay, let's open this book here. Okay. So you can go to the chapter 5 here. Okay, before we go to the chapter 5, I think there's important information. I think that will be also helpful to you. Let's go to the top page, okay, which is the title page. If you go down below here, down below here, just a minute. Okay, so there's additional resources. Additional resources. Check out the additional resources. The online supplementary materials exist at this website. Okay, so let's click this up and open this link and see what's inside there. Okay, so if you click this, and you can also check the data set exercise not available. Oh, okay. I think it should be here. Okay, so there's a quick start here. If you want to reproduce the code in the book without having to install anything, you can go to the book cloud. Okay, book cloud should be here, right? No, not this one. This one. Give me a minute. Oh, I think it should be here, right? Should be here. Okay, all you have to do, let me repeat again. You go to the supplementary material here, and because now we are discussing chapter 5, so you go to the logistic regression, okay? Go to the logistic regression, and then you click it. Okay, so now you can see all the codings available here. Okay, the interesting thing is that because we have some plugins and tables, for example, being generated on this cloud webhook. But if you want to replicate the codings, and if you want to regenerate the same output as you see on the cloud, you can copy the codings here and rerun this coding to generate the plots. So for example, I myself like these codings very much. For example, if you want to generate this plot, okay, if you want to generate this plot, all you have to do is just to copy the codings here, and generate plots. Then you can generate plots down below. Okay, so all codings are available here, so you can follow these codings, and finally you can generate the plots. Okay, but if you just check out books, okay, you go to the logistic regression here. If you check out the books, and you won't be able to see the codings. For example, it just show you the plots. Okay, but if you want to replicate or regenerate the plots like this, okay, you have to go back to this materials, okay, and you can regenerate the plots. So this is very good codings for your reference. So I like it very much. So this is just for your reference, and I think that will be very helpful to you. Okay, so for example, like this one, if you want to generate the PDP or partial dependence plot, okay, then you can just because this the author has already generated the functions, so that you can just apply these functions immediately, okay, without taking you too much time here. Okay, so this is just for reference here. Okay. So remember where to find the materials. Okay, just to go to the here. Okay, basically you need to find this website. Okay, hands-on machine learning with R. Okay, so let's take a break and we'll be back later.